Hello there, and welcome back to Bedtime Science. I'm really glad you're here tonight. Memory is one of the quiet miracles of the brain. It is the reason a voice can feel familiar after years of silence. It is the reason a room can become meaningful, the reason a song can carry an entire season inside it, the reason a scent can suddenly return you to a kitchen, a street, a school hallway, or a summer afternoon you had not thought about in decades. Memory is not only a storage system. It is the way the past remains available to the present. Inside the human skull, in about 1.5 kilograms of living tissue, the brain builds and rebuilds the record of a life. It does this with roughly 86 billion neurons, trillions of synapses, waves of electrical activity, chemical signals, changing proteins, growing and shrinking connections, and patterns that are constantly being shaped by attention, sleep, emotion, repetition, and time. Every name you know, every skill you use without thinking, every route through a familiar town, every warning learned from pain, every fact, every habit, every private image of someone you love, depends on this soft, restless architecture. And yet memory is not a perfect archive. It is not a library where every book stays exactly where it was first placed. It is not a recording device that quietly captures reality and plays it back without alteration. Memory is alive. It is selective, constructive, vulnerable, and useful. It preserves some things with astonishing force and lets other things vanish almost immediately. It can protect, mislead, comfort, embarrass, guide, and surprise us. It helps make a person feel continuous across time, while also constantly rewriting that continuity in light of the present. Tonight, we move gently through the quiet science of memory, how the brain encodes experience, how memories are stabilized, why sleep matters, why forgetting is not always failure, why emotional moments can remain so vivid, why eyewitness memories can be wrong even when they feel certain, and why remembering the past and imagining the future use many of the same neural systems. The science is detailed, but the central wonder is simple. Somehow, matter learns from time. Memory begins with attention. At every moment, the senses deliver more information than the brain could possibly store. Light, sound, pressure, temperature, smell, body position, internal sensations, fragments of language, movement in the edges of vision, the emotional tone of a face, the rhythm of breathing, the texture of a surface under the fingers. Most of this disappears almost instantly. The brain is not designed to remember everything. It is designed to select. Attention is the first gate through which experience must pass. This is why two people can live through the same moment and remember different worlds. One remembers the color of the walls. Another remembers the exact sentence someone said. Another remembers only the feeling in the room. What enters memory depends on where attention rested, what seemed important, what connected to earlier knowledge, what carried emotional weight, and what the brain was prepared to notice. Memory is not made after experience is finished. It begins while experience is still unfolding. The first trace of sensory experience can be astonishingly brief. Iconic memory, the short-lived visual register, may hold a large amount of visual information for less than a second. Echoic memory, the brief auditory register, can hold the tail of a sound for a few seconds, which is why you may ask someone to repeat a sentence and then, before they do, realize you heard it after all. These sensory stores are not long-term memories. They are more like fading impressions at the doorway of awareness, giving the brain a moment to decide what matters. From there, some information enters working memory, the active mental workspace that allows you to hold a phone number long enough to type it, compare two ideas, follow a sentence, solve a problem, or remember the beginning of a thought while you reach its end. Working memory is not simply a small shelf for temporary storage. It is a dynamic system supported by networks involving the prefrontal cortex, parietal regions, and other areas that maintains and manipulates information in the service of thought. Working memory is limited, and that limitation shapes everyday life. People can usually hold only a handful of separate items in mind at once, though the number depends on how the material is organized. Chunking allows the brain to treat several pieces of information as a meaningful unit. A random string of digits is hard to remember. The same digits arranged as a familiar date, a known code, or a rhythmic pattern become easier. The brain remembers meaning better than isolated noise. This limited workspace is one reason thought can feel fragile at night when the mind is tired. A small interruption can erase what you were about to say. A new task can displace the old one. A door crossed at the wrong moment can leave you standing in a room wondering why you came there. These failures can be irritating, but they reveal something useful. Working memory is not a warehouse. It is more like a lamp, illuminating a small portion of mental content at a time. Long-term memory is not one system either. One of the oldest and most important distinctions is between explicit memory and implicit memory. Explicit memory, also called declarative memory, is memory you can bring into conscious awareness and often describe in words. It includes facts, events, names, dates, meanings, and personal experiences. Implicit memory, by contrast, changes behavior without requiring conscious recollection. It is present when fingers know a piano pattern before the mind names the notes, when a cyclist balances automatically, when a familiar route is driven almost without thought, or when an old fear returns before a clear memory of its source. Explicit memory can be divided again. Semantic memory is memory for knowledge, that Paris is the capital of France, that the heart pumps blood, that Jupiter is larger than Earth, that water freezes at a certain temperature under familiar pressure. Episodic memory is memory for events. A birthday dinner, a walk after rain, a conversation, a childhood room, a particular morning when the light fell across a table in a way you somehow still remember. Semantic memory tells you what you know. Episodic memory lets you mentally revisit a lived moment. The difference between semantic and episodic memory matters because the brain can treat them differently. A person may remember facts while losing access to recent personal events. Another person may preserve vivid experiences while struggling to name categories or recognize familiar concepts. In everyday life, the two are interwoven. A memory of visiting a museum may include both the event itself and facts learned there. Over time, the event may fade while the knowledge remains. You may know something without remembering when you learned it. The hippocampus is one of the central structures in the science of memory. Curved deep within each medial temporal lobe, shaped somewhat like a seahorse, the hippocampus is essential for forming many new explicit memories. It does not store every detail of every memory permanently in a simple way. Instead, it helps bind together the distributed pieces of an experience: the place, the people, the sounds, the meaning, the emotional tone, the sequence of events. It helps turn a passing moment into something that can be recalled later as an episode. The importance of the hippocampus became painfully clear through one of the most famous cases in neuroscience. Henry Molaison, known for decades as HM in 1953, surgery intended to treat severe epilepsy removed large portions of his medial temporal lobes, including much of the hippocampal region on both sides. The operation reduced his seizures, but it left him unable to form new long-term explicit memories. He could hold a conversation for a short time, but after a delay, the conversation vanished. He met researchers again and again as if for the first time. What made HM's case so scientifically powerful was not only what he lost, but what remained. His intelligence was broadly preserved. His personality was recognizable. He retained many older memories from before the surgery. Most strikingly, He could learn new motor skills without remembering that he had practiced them. In a mirror drawing task, his performance improved over repeated sessions, even though each session felt new to him. His brain could learn without conscious recollection. This showed that memory is not a single faculty, but a family of systems. The hippocampus is sometimes described as a memory index. Imagine an event as a pattern spread across the cortex. Visual areas representing what was seen, auditory areas representing what was heard, language areas representing words, emotional circuits representing feeling, body maps representing posture and movement. The hippocampus helps link these distributed elements so that a partial cue can later reactivate the whole pattern. A smell, a doorway, a phrase, or a piece of music may touch one strand and pull the rest of the memory back into awareness. Memory also depends on synapses, the tiny junctions where neurons influence one another. A neuron sends electrical impulses down its axon. At the synapse, chemical neurotransmitters cross a narrow gap and alter the activity of another neuron. Learning changes the strength of these connections. Some synapses become more effective. Others weaken. New spines can appear on dendrites. Old ones can shrink. The brain does not remember by placing miniature images inside neurons. It remembers by changing relationships among cells. One of the most studied forms of synaptic change is long-term potentiation, or LTP. When one neuron repeatedly helps activate another, the connection between them can become stronger for hours, days, or longer. This idea fits the principle often summarized as neurons that fire together wire together. The phrase is simple, but the biology is complex. NMDA receptors, AMPA receptors, calcium entry, intracellular signaling, gene transcription, protein synthesis, structural remodeling, and local changes at synapses all contribute to different phases of strengthening. The early phase of synaptic strengthening can happen quickly, using proteins already present at the synapse. The later phase, needed for longer-lasting changes, often requires new gene expression and protein synthesis. In other words, the brain does not merely receive experience. It responds by altering its own molecular machinery. A meaningful lesson, a repeated practice, or an emotionally powerful event can ultimately change which proteins are made, where receptors are placed, and how future signals will flow. This is one reason memory feels both mental and physical. A recollection may seem like a private image, a thought, a feeling, or a story, but underneath it are biological changes. Not a single simple storage location, not one tiny cabinet labeled with a name, but patterns of altered connectivity and excitability. Memory is distributed, layered, and dynamic. The memory of a face is not the face itself. It is a learned pattern that allows the brain to recreate recognition when the right cues appear. The word engram is used for the physical trace of a memory. For much of the 20th century, the engram was partly a scientific dream. Researchers knew memory had to leave some trace in the brain, but locating it precisely was difficult. Modern techniques, especially in animal studies, have made the concept more concrete. Scientists can identify groups of neurons that are active during learning and later reactivate during recall. In some experiments, stimulating these neurons can bring back behavior associated with a memory. This does not mean memories are stored in single cells like files and drawers. An engram is better thought of as a network, a pattern of cells that participate in representing and reactivating an experience. The same neuron may belong to more than one memory. Different memories may overlap. Recall may involve reassembling activity across many brain regions. The engram is not a frozen object. It is a living trace capable of being strengthened, weakened, linked, and updated. Encoding is the first major step in forming memory. It refers to the transformation of experience into a neural representation that that can later be stored and retrieved. Strong encoding usually requires attention, meaning, organization, and often emotion. Repetition helps, but repetition without attention can be weak. Deep processing helps more. If you think about how a word sounds, you may remember it less well than if you think about what it means, how it connects to something you already know, or how it applies to your own life. The brain is especially good at remembering organized information. A random list is difficult. A story is easier. Isolated facts fade. Facts connected to a larger framework survive better. This is why teaching often works best when it does not simply present information, but builds a structure in which information belongs. Memory is helped by meaning because meaning provides many paths back. A fact connected to other facts has more retrieval routes than a fact left alone. Emotion can strengthen encoding dramatically. The amygdala, a small almond-shaped structure involved in detecting emotional significance, interacts with the hippocampus and other systems during emotional learning. A threatening event, a joyful surprise, a humiliation, a moment of awe, or a sudden loss can be encoded more strongly than neutral events around it. Stress hormones and neuromodulators, such as norepinephrine, can enhance consolidation under some conditions, preparing the brain to preserve information that may matter for survival. But emotion does not turn memory into a perfect recording. It can sharpen central details while blurring peripheral ones. A person may remember the weapon but not the face, the insult but not the exact room, the fear but not the sequence. Emotional memories can be vivid and still be wrong in details. The feeling of certainty is not the same as accuracy. This distinction is one of the most important lessons of memory science. Flashbulb memories illustrate the paradox. People often remember where they were when they heard shocking public news, and these memories can feel extraordinarily vivid. The room, the voice, the screen, the person who spoke first. Yet studies following such memories over time show that details can change while confidence remains high. The emotional force of the event preserves the sense that the memory is clear, but the memory itself can still be reconstructed, revised, and filled in. Consolidation is the process by which memories become more stable over time. At first, a new memory can be fragile. It can be disrupted by interference, distraction, brain injury, certain drugs, or simply by the flood of later information. Over hours, days, and longer periods, biological processes stabilize it. At the synaptic level, this involves changes in proteins, receptor placement, and synaptic structure. At the systems level, it involves communication between the hippocampus and the neocortex. One influential model proposes that the hippocampus is especially important for newer episodic memories, while older memories gradually become more supported by distributed cortical networks. This process is not as simple as copying a file from one place to another. The hippocampus may remain involved in rich, detailed episodic recall, especially when memories require vivid reconstruction. But over time, the cortical representation of knowledge and familiar events can become less dependent on the hippocampus. The past settles into the wider brain. Sleep is one of the great allies of memory. After learning, sleep can improve retention, not merely because the brain is resting, but because it is active in a different way. During slow-wave sleep, patterns of activity associated with recent experience can be replayed, especially in hippocampal cortical networks. Slow oscillations, sleep spindles, and sharp wave ripples appear to help coordinate the dialogue between temporary and longer-term storage systems. The sleeping brain is not turned off. It is quietly organizing. This makes sleep feel almost poetic. During the day, the brain receives the world. During sleep, it sorts, strengthens, weakens, integrates, and sometimes transforms what was received. Not every detail is preserved. Some traces are allowed to fade. Some are linked to older knowledge. Some emotional material may be processed in altered neurochemical conditions. Dreams may not be simple memory replay, but dreaming shows how freely the brain can recombine fragments of experience into new scenes, meanings, and associations. REM sleep and non-REM sleep likely contribute differently to memory, and the exact roles are still studied. Declarative memories often benefit from slow-wave sleep. Emotional learning and procedural learning may be influenced by REM sleep and by the full architecture of sleep across the night. The important point is not that one stage has one simple job. The night is a sequence of changing brain states, and each state may provide a different environment for different kinds of memory processing. Forgetting is often treated as a failure, but forgetting is also necessary. A brain that remembered every detail with equal force would be overwhelmed. It would struggle to generalize, to prioritize, to update, to live in the present. Forgetting clears space, reduces interference, and allows memory to remain useful rather than merely complete. The goal of memory is not total preservation. The goal is adaptive guidance. The forgetting curve, first studied systematically by Hermann Ebbinghaus in the 19th century, shows that forgetting is usually fastest soon after learning and then slows. Information that is not revisited, used, connected, or emotionally marked can fade quickly. This pattern can feel discouraging, but it also reveals how to strengthen memory. Spacing learning over time works better than cramming because each return to the material forces the brain to retrieve and rebuild the trace. Retrieval practice is one of the most powerful learning methods discovered by cognitive psychology. Trying to remember something strengthens memory more than simply looking at it again. The act of retrieval is not passive. It changes the memory, improves access, and often reveals what is missing. This is why self-testing can be more useful than rereading, even when rereading feels smoother. Learning that feels easy is not always learning that lasts. There is a category of learning conditions called desirable difficulties. These are challenges that make learning feel harder in the moment, but improve long-term retention. Spacing practice, interleaving topics, varying context, and testing oneself can all slow down the feeling of fluency while increasing future memory. The brain benefits from effortful retrieval because effort creates stronger routes back to the information. The path that is walked with difficulty may become easier to find later. Context matters too. A memory is often easier to retrieve when the external or internal context resembles the one in which it was learned. A room, a smell, a mood, a song, or even a body state can become part of the retrieval queue. This is why returning to a childhood place can release memories that seemed absent. The place supplies cues the mind had not generated on its own. The memory was not gone. The key was missing. Smell has a special relationship with memory because olfactory information has direct routes into limbic regions involved in emotion and memory. A scent can bypass ordinary verbal searching and bring back a moment with surprising intensity. The smell of rain on warm pavement, a particular soap, old books, cut grass, smoke, bread, perfume, hospital disinfectant, or a wooden drawer can carry time inside it. The memory may not arrive as a sentence. It may arrive first as atmosphere. Music also binds memory powerfully. A song can preserve not only lyrics or melody, but the feeling of an era of life. People with dementia who struggle with recent conversation may still sing songs learned decades earlier. Music engages widespread brain networks: auditory, motor, emotional, predictive, and autobiographical. Rhythm and melody provide structure, repetition, and emotional salience. A song is a memory machine disguised as sound. Procedural memory is the memory of how to do things. It includes motor skills such as typing, swimming, riding a bicycle, playing an instrument, tying a knot, or using tools. These memories depend heavily on systems involving the basal ganglia, cerebellum, motor cortex, and related circuits. They often require practice over time and can remain accessible even when explicit memory is damaged. This is why a person can perform a learned action without being able to explain exactly how. Procedural memory can feel mysterious because skilled action becomes partly invisible to consciousness. A pianist does not consciously command every finger movement. A driver does not calculate every correction of the wheel. A dancer does not name every muscle. Practice transfers control into circuits that operate below the level of deliberate thought, freeing attention for expression, strategy, or environment. Skill is memory made fluent. Habits are related but not identical to skills. A habit is a learned behavior triggered by a cue and reinforced by a reward or outcome until it becomes automatic. Habits can be useful because they reduce cognitive effort. They can also be difficult to change because the cue can trigger the behavior before deliberate intention fully engages. The basal ganglia are central to habit learning, helping actions become linked into routines. Much of daily life is built from remembered sequences the mind does not need to supervise. Implicit memory also includes priming. If you see or hear a word, image, or concept, you may process related information more easily later, even without remembering the first exposure. Priming shows that the past can influence behavior without entering conscious recall. A person may prefer a shape, complete a word stem, recognize a pattern, or respond faster because of something encountered earlier that they do not remember encountering. Memory can be present even when remembering is absent. Classical conditioning is another form of implicit memory. If a neutral stimulus is paired with something biologically important, the neutral stimulus can begin to evoke a response. A sound paired with danger can later provoke fear. A taste followed by nausea can become aversive after a single experience. These forms of learning can be powerful because they serve survival. The body remembers what the conscious mind might prefer to forget. Fear memory has been studied extensively because it reveals how emotional learning can become durable and sometimes harmful. The amygdala helps link cues to threat. The hippocampus helps encode context. The prefrontal cortex helps regulate responses and update learning when danger has passed. In healthy learning, fear can be adjusted when new evidence shows safety. In anxiety disorders or trauma-related conditions, fear memories can become intrusive, overgeneralized, or resistant to updating. Post-traumatic stress disorder is not simply having a bad memory. It involves intrusive recollections, physiological arousal, avoidance, mood changes, and altered threat processing. Traumatic memories may return as fragments, images, sensations, sounds, bodily reactions, or emotional states. Research on reconsolidation and extinction has inspired therapies that aim to help the brain update the meaning and emotional power of traumatic memories. The goal is not to erase a life event, but to reduce its ability to dominate the present. Reconsolidation changed how scientists think about remembering. A memory, once consolidated, was once thought to be fixed. But research has shown that when a memory is reactivated, it may enter a temporarily unstable state, during which it can be modified before being stored again. This means remembering is not merely reading an old record. It can be an act of rewriting. Every recall may carry the possibility of change. This helps explain why stories change with retelling. Each time a person remembers an event, the current context, emotions, beliefs, and later knowledge can influence the reconstruction. Details may be added, softened, sharpened, or reorganized. The person may not be lying. They may be remembering sincerely, but memory is not sealed away from the present. It is updated by the mind that retrieves it. False memories are therefore not rare curiosities. They are natural risks of a constructive system. Elizabeth Loftus and other researchers showed that misleading information after an event can alter what people later report remembering. A question phrased in a certain way can change speed estimates, introduce objects that were not present, or increase confidence in details that never occurred. The mind often fills gaps with what seems plausible, and later may mistake that construction for perception. This has enormous importance for eyewitness testimony. A witness can be honest, confident, and wrong. Stress, poor viewing conditions, cross-racial identification difficulties, suggestion, repeated questioning, feedback from investigators, media exposure, and time can all influence recall. The legal system has had to confront the fact that memory confidence is not a perfect measure of memory accuracy. Science does not say eyewitnesses are useless. It says they are human. The constructive nature of memory may sound like a flaw, but it is also what makes memory flexible. A video recording can only replay. A human memory can summarize, infer, connect, and generalize. It can extract lessons from many experiences and apply them to a new situation. It can imagine what might happen next. The same system that makes memory vulnerable to distortion also allows it to support creativity, planning, empathy, and meaning. Autobiographical memory is the memory system that carries the story of a life. It includes specific episodes, repeated events, life periods, personal themes, relationships, losses, achievements, ordinary routines, and turning points. It is organized partly like a timeline, partly like a narrative, and partly like a landscape of emotional significance. You do not remember your life as a complete recording. You remember selected scenes, and the mind uses them to maintain a sense of who you are. This autobiographical story is not fixed. A memory that once felt like failure may later become evidence of resilience. A painful ending may later be understood as a beginning. A childhood scene may gain meaning only in adulthood. The events did not change, but their place in the story did. Memory and identity shape one another. We remember through the self we are now, and the self we are now is partly built from what we remember. The reminiscence bump is one of the most interesting patterns in autobiographical memory. Adults often recall a disproportionate number of memories from adolescence and early adulthood, roughly the years when identity, independence, love, work, travel, education, and major firsts are often forming. These years provide novelty, emotional intensity, and self-defining experiences. The brain does not store them as important because they are early on a calendar. It stores them because they help build the person who will later look back. Infantile amnesia is the opposite mystery. Most adults remember little or nothing from the first years of life, even though early childhood is filled with learning. During those years, the brain learns faces, voices, movements, words, categories, social patterns, and emotional expectations. But the kind of explicit autobiographical memory adults can later narrate is sparse. The hippocampus and prefrontal cortex are still developing, language is limited, and the stable narrative self is not yet fully formed. This does not mean early life is forgotten in every sense. Early experiences can shape attachment, emotion regulation, habits, preferences, fears, and expectations without becoming conscious episodes. A person may not remember being soothed, but the nervous system may have learned what safety feels like. A person may not remember early stress, but the body may have adapted to it. Memory begins before autobiography. Semantic memory grows throughout life. It is the vast network of meanings, facts, concepts, words, categories, and relationships that makes the world understandable. You know what a chair is without remembering the first chair you saw. You know what winter means, what a promise means, what a city means, what a melody means, because the brain has abstracted patterns from many experiences. Semantic memory is experience distilled into knowledge. Language depends heavily on semantic memory. Every word carries associations, sounds, meanings, emotional tones, contexts, grammatical roles, images, and personal histories. The word ocean may mean a body of salt water, but it may also carry memories of beaches, ships, storms, childhood holidays, films, books, or fear. Meaning is layered. The dictionary gives one kind of memory. A life gives another. Names are a special challenge for memory. A person's face may be familiar, their voice recognizable, their history partly accessible, and still the name may not come. Proper names are often arbitrary labels, less connected to semantic meaning than common nouns. This makes them vulnerable to retrieval failure. The tip of the tongue state can be especially common for names, when the memory feels close but inaccessible, as if the mind is standing outside a locked door. The tip of the tongue phenomenon reveals that retrieval can be partial. You may know the first letter, the rhythm, the number of syllables, or related information, while still failing to produce the word itself. Memory is not all or nothing. Different components of a memory can be accessed separately: sound, meaning, image, context, source, emotional tone. Retrieval is a coordinated act, and sometimes one piece arrives without the others. Source memory is the ability to remember where information came from. It is crucial because knowing a fact is different from knowing how you know it. Did you hear it from a trusted expert, read it in a novel, imagine it, dream it, see it online, or infer it yourself? Many memory errors are source errors. The content may feel familiar, but its origin is misattributed. This is one reason misinformation can spread so easily. Familiarity can be mistaken for truth. The brain uses familiarity and recollection differently. Familiarity is the sense that something has been encountered before. Recollection is the richer retrieval of details about the encounter. You may see a face and feel it is familiar without knowing where from. Or you may remember the dinner, the conversation, and the person's name. Familiarity is fast and useful, but it can be misleading. Recollection is richer, but also more fragile. Déjà vu is a strange case of familiarity without a clear source. A new situation suddenly feels as if it has happened before. The experience can be vivid and uncanny, but it usually does not indicate a real memory. It may arise from a mismatch between familiarity signals and recollection, or from brief disruptions in temporal lobe processing. Déjà vu reminds us that the feeling of remembering can be separated from the actual retrieval of a past event. Spatial memory is one of the most ancient and powerful forms of memory. Animals need to remember where food is found, where danger appeared, where shelter lies, where territory begins, how to return home. In humans, spatial memory supports navigation through cities, houses, landscapes, and imagined places. It also supports abstract thought. We speak of being close to an idea, far from a conclusion, on the right path, or lost in thought. Space becomes a metaphor because the brain is built to move through worlds. The hippocampus is deeply involved in spatial memory. Place cells fire when an animal is in a particular location. Grid cells in the entorhinal cortex fire in repeating patterns that form something like an internal coordinate system. Head direction cells, border cells, and other spatial signals help the brain know where the body is and how it is oriented. These discoveries showed that memory and navigation are intertwined. To remember is often to locate. The method of loci, or memory palace, takes advantage of this spatial strength. By placing information along a familiar imagined route, a person can use spatial memory to support recall of words, numbers, speeches, or lists. Ancient orators used such techniques long before modern neuroscience could explain why they worked. A familiar hallway, a childhood home, or an imagined palace becomes a scaffold for otherwise abstract material. The mind remembers places, and information attached to places becomes easier to find. Memory also depends on prediction. The brain is constantly comparing what happens with what it expected. Surprises are often remembered because they signal that the model of the world needs updating. A routine commute may disappear from memory because nothing violated expectation. A single unusual moment on that commute may remain for years. Novelty tells the brain, pay attention, this may matter. This is why travel can feel so memorable. New streets, languages, foods, smells, schedules, and social cues require attention. The brain cannot run entirely on habit. It encodes more because more needs to be learned. Later, a 3-day trip may feel longer in memory than an ordinary month, not because it contained more clock time, but because it contained more novelty and more distinct scenes. Memory compresses repeated experience. If you take the same route every day, the individual days may blur into a general memory. This is efficient. The brain does not need to store every identical staircase, every identical door, every identical cup of coffee. It builds schemas, general structures that capture what usually happens. Schemas help comprehension and prediction, but they also shape recall. We may remember what usually happens rather than what actually happened once. Schemas are powerful in learning. New information is remembered better when it can attach to an existing schema. A chess expert remembers a meaningful board position far better than a beginner because the expert sees patterns, threats, and plans, not isolated pieces. A doctor remembers symptoms in relation to diagnostic frameworks. A musician hears harmonic structure. Expertise changes memory because expertise changes perception. The prefrontal cortex helps organize memory strategically. It supports attention, working memory, retrieval search, monitoring, and inhibition of irrelevant information. When you try to remember a name, check whether a memory is accurate, separate imagination from reality, or choose the right detail from many possible ones. Frontal systems are heavily involved. Memory is not only storage, it is control. The brain must decide what to retrieve and whether to trust it. Aging affects memory in uneven ways. Normal aging often brings more difficulty with working memory, processing speed, source memory, and recent episodic memory. Names may become harder to retrieve. Multitasking may feel more demanding, but semantic knowledge can remain strong or even grow, and procedural skills can remain resilient. Older memory is not simply worse memory. It is a changed landscape, with some paths worn deep and others harder to access. The difference between normal aging and disease matters. Forgetting why you entered a room can happen at any age. Taking longer to recall a name can be normal. But progressive impairment that disrupts daily life, repeats the same questions, causes disorientation, changes judgment, or interferes with familiar tasks can signal something more serious. Alzheimer's disease and other dementias attack memory and cognition through disease processes, not ordinary forgetfulness. Alzheimer's disease often begins by damaging systems important for forming new episodic memories, including the hippocampus and entorhinal cortex. A person may repeat questions, misplace objects, forget recent conversations, or struggle to remember new information. Older memories may remain accessible longer because they are more distributed and consolidated, but as the disease progresses, language, reasoning, recognition, and daily functioning can also be affected. Memory loss in dementia is not just the loss of facts. It can become the loss of orientation in one's own life. At the biological level, Alzheimer's disease involves amyloid beta plaques, tau tangles, inflammation, synaptic dysfunction, and neuronal loss. The relationship between these processes is complex, and research continues to refine how the disease begins and progresses. Recent treatments targeting amyloid can modestly slow decline in some early-stage patients, but they are not cures and carry risks. For a bedtime science story, the important point is human and scientific at once. Memory depends on delicate living networks, and when those networks are damaged, the continuity of self can be shaken. Memory is not confined to humans. Animals remember in many ways suited to their lives. Scrub jays can remember what food they cached, where they cached it, and how long ago. Information that matters because some foods spoil faster than others. Rats navigate mazes and remember safe and dangerous places. Bees remember flower locations and communicate through dances. Octopuses learn to solve problems. Dogs remember routines, voices, places, and social cues. Memory is not one human gift, but a broad biological strategy. Some animals have extraordinary specialized memories. Food caching birds can store thousands of seeds and recover many of them months later. Migratory species remember routes across continents and oceans. Salmon return toward natal streams through a combination of smell, magnetic cues, and navigation. Elephants remember water sources and social relationships across long periods. Each species remembers what evolution made important for its way of life. Human memory, however, has an unusual relationship with storytelling. We do not only remember where food is or which sound predicts danger. We make narratives, histories, explanations, promises, identities, and imagined futures. A human memory can become a lesson, a confession, a joke, a warning, a family story, a myth, a scientific observation, or a piece of art. We externalize memory into language, writing, photographs, maps, calendars, monuments, songs, and now digital archives. Writing changed memory by allowing information to live outside the brain. A shopping list, a diary, a law code, a scientific paper, a family photograph, a gravestone, a recipe, a library, a database, all are external memory systems. They do not replace biological memory. They change what biological memory must do. Instead of holding every detail, the mind can remember how to find, interpret, and use stored information. Digital memory has changed this again. Phones remember appointments, faces, routes, messages, photographs, songs, locations, and search histories. This can free the brain from some burdens, but it may also change attention and encoding. A photographed moment is not always better remembered by the person who photographed it, especially if taking the picture replaces careful attention. External memory is useful, but the brain still needs presence to build lived memory. There is a difference between preserving data and remembering experience. A camera can store an image with more visual detail than the mind, but the mind stores significance, why that moment mattered, how the air felt, who was missing, what was hoped for, what changed afterward. A digital file can keep pixels. Memory keeps meaning, though imperfectly. Sometimes a blurred memory is more personally true than a perfect photograph because it carries the emotional shape of the moment. Attention in modern life is often fragmented, and fragmented attention can weaken memory. If a person checks messages while listening, scrolls while watching, or switches constantly between tasks, encoding becomes shallow. The brain may recognize that something occurred but fail to bind it into a durable memory. Multitasking often feels productive, but much of it is rapid task switching, and each switch has a cost. Memory needs not only time, but contact. Stress has a complicated relationship with memory. Moderate arousal can enhance memory for important events. Severe or chronic stress can impair hippocampal function, disrupt sleep, reduce attention, and bias the brain toward threat. Acute stress may strengthen central emotional details while weakening context. Chronic stress can make the mind more reactive and less flexible. The memory system evolved to help organisms survive, but survival states are not always ideal states for learning. The body is part of memory too. Interoception, the sensing of internal bodily states, contributes to emotion and recall. A racing heart, tight stomach, Relaxed breath, tired muscles, or warmth in the chest can become part of how a moment is encoded. Later, a similar body state can help bring back a memory or mood. This is why memory is not purely mental in the everyday sense. The brain remembers as part of a body. Place attachment shows how memory can make environments feel alive. A house is not merely walls when it holds years of meals, arguments, mornings, repairs, footsteps, celebrations, and quiet hours. A street can become layered with former versions of the self. A city can feel familiar because memory has mapped it emotionally as well as spatially. We live not only in physical places, but in remembered places. Memory also shapes relationships. To know someone is partly to remember them. Their voice, preferences, history, humor, fears, gestures, promises, and patterns. Love depends on memory, not only in the sentimental sense, but in the practical one. You remember what comforts someone, what hurts them, what they told you years ago, what they are trying to become. Shared memory creates intimacy. A relationship is partly a private archive held by more than one mind. Grief shows the depth of this. When someone dies, the memory system continues to expect them. A familiar sound may briefly seem like them. A place may hold their absence as strongly as it once held their presence. Memories become both comfort and pain. Over time, grief may change not because the memories disappear, but because their emotional organization changes. The person becomes part of an inner world that can be visited without the same raw shock each time. Memory can also be moral. Remembering harm can protect. Remembering kindness can guide. Remembering mistakes can lead to repair. Cultures build collective memory through rituals, histories, museums, anniversaries, and stories because groups, like individuals, need continuity and warning. But collective memory is also selective and can be distorted. Societies, like brains, remember through present needs. The science of memory, therefore, has consequences beyond the individual. One of the gentlest truths in memory science is that a memory does not need to be dramatic to matter. Many lasting memories are small. A hand on a shoulder, the sound of dishes in another room, a lamp in winter, a dog sleeping at someone's feet, a sentence that gave courage, a road at dusk, a classroom window, a grandmother's kitchen, a train station, a notebook, the smell of pencil shavings, the first quiet morning after a difficult season. The brain is not only an instrument for danger and survival, it is also an instrument for tenderness. Why some small moments last is not always clear. They may be emotionally marked, repeated in thought, connected to identity, or preserved by later meaning. Sometimes a memory becomes important only because we return to it. Rehearsal is not always deliberate study. It can be private revisiting. A person may carry a scene for years because it became part of how they understand themselves. Memory is partly biology, partly attention, and partly the stories we continue to tell inwardly. Future thinking depends on memory. When you imagine tomorrow, plan a conversation, picture a journey, or worry about an outcome, the brain uses pieces of past experience to construct possible futures. The hippocampus, which helps bind past episodes, is also involved in imagining new scenes. People with severe amnesia often struggle not only to remember the past, but to imagine detailed future experiences. Without memory, the future becomes less richly buildable. This connection between memory and imagination is profound. The brain does not store the past simply to admire it. It stores the past to prepare. It uses memory to simulate, predict, choose, avoid, approach, and create. The same constructive system that can distort recall allows the mind to build futures that have never existed. Memory is the raw material of imagination. Creativity often depends on recombination. A composer remembers sounds, structures, and feelings, then arranges them in a new way. A scientist remembers findings, models, failures, and analogies, then sees a connection. A writer remembers voices, places, conflicts, and rhythms, then creates a scene. New ideas do not come from nowhere. They arise when memory fragments meet under the right conditions. The brain must balance stability and plasticity. If it were too stable, learning would be impossible. If it were too plastic, old knowledge would dissolve. Memory requires a system that can change without losing itself. Synapses must be adjustable, but not chaotic. Networks must learn new patterns while preserving old ones. Sleep, attention, neuromodulators, inhibition, and consolidation all help maintain this balance. There is also competition in memory. Similar memories can interfere with one another. Learning a new password can make the old one harder to recall, and the old one can intrude when you try to use the new one. Similar names, routes, languages, or procedures can overlap. The brain must separate patterns enough to avoid confusion while linking them enough to generalize. This process, often discussed in terms of pattern separation and pattern completion, is one of the hippocampus's important roles. Pattern separation helps distinguish similar experiences. It is what allows the brain to remember where the car was parked today, not merely where it is usually parked. Pattern completion allows a partial cue to retrieve a whole memory. A few notes can bring back a song. A doorway can bring back a house. One face in a photograph can bring back an entire period of life. Too little separation causes confusion. Too little completion leaves memories inaccessible. Neurogenesis in the adult hippocampus has been a subject of intense study and debate. In some animals, new neurons are clearly generated in the dentate gyrus and appear to contribute to learning, pattern separation, and mood regulation. In adult humans, the extent and functional importance of hippocampal neurogenesis remains more controversial, with different studies reaching different conclusions. This is a good example of science in progress. Memory research contains solid foundations, but also living questions. Another living question is how exactly subjective experience arises from neural activity. Scientists can study synapses, circuits, systems, behavior, and brain imaging. They can see which regions activate during encoding or retrieval. They can disrupt certain processes and observe memory changes. But the felt quality of remembering, the sudden return of a scene, the warmth of recognition, the ache of nostalgia, is still difficult to explain fully. Neuroscience can map many mechanisms without exhausting the mystery of experience. Nostalgia is one of memory's emotional colors. It is not simply sadness for the past. It often combines longing, warmth, loss, gratitude, and identity. A nostalgic memory may comfort by reminding a person that life has had meaning and continuity. It may also hurt by making time visible. The same memory can be sweet and painful because it proves that something mattered and that it has changed. Memory is shaped by culture. Different cultures encourage different kinds of autobiographical recall. Some emphasize individual achievement and personal preference. Others emphasize family, community, duty, and social context. Parent-child conversations influence how children learn to narrate their experiences. A child whose memories are elaborated with questions and emotion may develop a different autobiographical style from a child whose experiences are discussed more briefly. The brain is biological, but remembering is also social. Conversation is one of the ways memories are stabilized and transformed. When people tell stories together, they cue one another, correct one another, and sometimes reshape one another's memories. Families develop shared versions of events. Friends preserve details one person might have lost, but group remembering can also introduce errors. A confidently told detail can spread through a group and become part of everyone's memory. Memory is contagious because humans remember together. Education is, in one sense, applied memory science. A teacher is trying to help knowledge survive beyond the moment of explanation. The best learning usually combines attention, meaning, retrieval, spacing, feedback, emotion at a manageable level, and connection to prior knowledge. Cramming can produce short-term performance, but spaced retrieval builds lasting access. A quiet truth of education is that forgetting is not defeated by intensity alone. It is defeated by returning. There is comfort in this. To learn something deeply, one does not need to force the brain into perfection in one sitting. The brain likes revisiting. It likes sleep between attempts. It likes meaningful connections. It likes testing itself gently. It likes effort that is not panic. Memory grows best when experience has time to settle. The brain also remembers what is rewarded. Dopamine, often oversimplified as a pleasure chemical, plays major roles in learning, motivation, prediction error, and reinforcement. When outcomes are better or worse than expected, dopamine systems help update future behavior. This is central to reinforcement learning. The brain learns not only what happened, but whether it was worth doing again. Addiction can be understood partly as maladaptive learning. Drugs, gambling, and other powerful rewards can reshape circuits involved in motivation, habit, and memory. Cues associated with the reward can trigger craving long after the immediate experience. A street, smell, time of day, emotion, or social context can reactivate learned associations. Recovery often requires not only willpower, but new learning, new cues, new routines, and time for old associations to weaken. Memory can be strengthened by emotion, but it can also be protected by calm. Panic can narrow attention. Overwhelm can impair encoding. A moderate level of interest, curiosity, and emotional engagement often helps learning more than fear. This matters because people sometimes try to force memory through pressure when the brain may need safety to organize information well. The best memory is not always made under intensity. Sometimes it is made under quiet attention. The immune system and memory interact in ways scientists are still exploring. Inflammation can affect mood, cognition, sleep, and neural function. Illness can make thinking foggy and memory less reliable. Chronic inflammatory states may influence brain health. The brain is not isolated from the body. It is nourished, protected, and affected by bodily systems. Memory depends on blood flow, metabolism, hormones, immune signaling, and sleep. It is a whole-body achievement. Exercise supports brain health through multiple pathways: improved blood flow, metabolic regulation, sleep quality, mood, and factors that support neuroplasticity. Physical activity is associated with better cognitive aging and may support hippocampal function. This does not mean memory can be solved with one lifestyle rule, and it should not be reduced to simplistic advice. But the brain evolved in a moving body, and movement remains one of the quiet supports for cognition. Nutrition, too, matters in broad ways. The brain needs energy, micronutrients, vascular health, and metabolic stability. But memory science is often misused to sell miracle supplements. The evidence for most memory pills is far weaker than the evidence for sleep, learning strategy, physical activity, social engagement, and management of cardiovascular risk factors. The brain is complex, and complex systems rarely yield to simple commercial promises. Social connection is also part of cognitive health. Conversation, shared activities, emotional support, and belonging all engage memory systems. Remembering with others helps maintain identity. Loneliness and isolation can increase stress and reduce cognitive stimulation. A human brain is not built only for individual storage. It is built for social worlds where memory is exchanged, confirmed, challenged, and loved. There is a quiet elegance in how memory makes ordinary life possible. You wake and know where you are. You recognize your own hands. You understand the room. You know how to stand, how to walk, how to open a door, how to use language, how to make coffee, how to read a message, how to return to a task. Nearly all of this depends on memory, and nearly all of it happens without ceremony. Memory is so constant that it becomes invisible. When memory fails briefly, its invisibility is revealed. A misplaced key, a forgotten name, a word that vanishes mid-sentence, a familiar street that suddenly seems strange, a password replaced by the old one. These moments can be frustrating, but they show how much the mind usually accomplishes. The brain is not failing because it forgets sometimes. It is succeeding because it remembers enough to make forgetting noticeable. Dreams may help memory in indirect ways. They often combine recent residues with older themes, emotional concerns, and imagined scenarios. A dream is not usually a literal replay of the day, but it can reveal the brain's tendency to weave fragments together. Some dreams may reflect emotional processing. Some may be noise shaped into narrative. Some may support creativity. The exact functions of dreaming remain debated, but sleep as a whole clearly matters for memory. During deep sleep, the brain can replay patterns from waking experience at compressed timescales. In rodents, sequences of hippocampal place cell activity that occurred while navigating a maze can reappear during rest and sleep. This replay may help strengthen and reorganize memory. The idea is beautiful. The brain, after moving through the world, moves through it again in darkness, not with muscles, but with patterns. Memory consolidation during sleep is not simply saving everything. It is selective. Emotional salience, reward, future relevance, repetition, and existing schemas all influence what is strengthened. The brain appears to prioritize. It may preserve what seems useful, meaningful, unresolved, or connected. This selectivity is why sleep does not make every moment equally memorable. It helps the archive remain shaped rather than flooded. The phrase memory trace can make memory sound delicate, like a footprint in sand. In some ways it is delicate. In other ways it is remarkably durable. People can recall childhood scenes after half a century. A song learned young can survive into old age. A language not spoken for years can return faster than it was first learned. The brain's traces can weaken, but they can also persist in hidden forms, waiting for the right cue, context, or practice. There is also memory in the body in the ordinary language of muscle memory, though muscles themselves are not storing the full skill. The nervous system has learned patterns of control. Repetition tunes circuits so that movement becomes smoother, faster, and more reliable. The body feels as if it remembers because the brain, spinal cord, sensory feedback loops, and muscles act together as a trained system. A practiced movement is a remembered coordination. Language learning shows memory's layers clearly. Vocabulary requires semantic memory. Pronunciation requires auditory and motor memory. Grammar becomes partly procedural with practice. Conversation requires working memory, attention, prediction, social memory, and emotion regulation. A new language at first feels effortful because every piece must be held consciously. Over time, patterns become automatic. What was once studied becomes lived. Memory for faces is another specialized skill. Humans are highly social, and recognizing individuals matters. Face processing relies on networks, including regions of the temporal lobe, and damage to these systems can produce prosopagnosia or face blindness, in which a person may see a face clearly but fail to recognize whose it is. This shows again that perception and memory are intertwined. Recognition is not just seeing, it is seeing connected to stored identity. Memory for emotions can outlast memory for facts. A person may forget the exact words spoken in a conversation, but remember feeling dismissed or understood. They may forget the details of a place, but remember that it felt safe. This can be useful because emotional summaries guide future behavior. It can also be unfair because the summary may survive after context is lost. Emotional memory is powerful, But like all memory, it benefits from reflection. Reflection can reshape memory. Journaling, therapy, conversation, art, and quiet thought can help place events into a larger frame. This does not necessarily change what happened. It changes how the memory is connected. A painful memory linked only to shame may become linked to survival, learning, injustice, compassion, or strength. Reconsolidation, narrative, and meaning-making may all play roles in how memories become easier to carry. There is no single location where the self sits and reads the memory archive. The self is more like an ongoing process, built from body signals, perception, goals, social feedback, habits, language, and autobiographical memory. Memory gives continuity, but continuity is an active achievement. Each morning, the brain reorients. This is my room, my body, my name, my history, my unfinished work, my people, my world. Identity is renewed through remembering. The fragility of memory makes compassion necessary. People forget birthdays, names, promises, instructions, and details not always because they do not care, but because attention failed, stress intervened, sleep was poor, or too many demands competed. This does not remove responsibility, but it softens judgment. The human memory system is powerful, but it is not perfect, and pretending it should be perfect only creates unnecessary cruelty. Memory also teaches humility about the past. What feels obvious in recollection may be partly reconstructed. What feels certain may have changed. The mind prefers coherent stories, and it may smooth rough edges to make them. This does not mean we cannot trust memory at all. It means trust should be thoughtful. Strong memories deserve respect, but they are not immune to question. Scientific memory, unlike personal memory, is protected by method. Notes, replication, measurement, peer review, data, and instruments exist because individual memory is not enough. Science is a collective system for remembering the world more accurately than any one mind could. A lab notebook is a defense against forgetting. A dataset is a memory externalized. A published result is an invitation for others to check whether the memory of nature has been recorded correctly. The history of memory research itself is a chain of remembered insights. Ebbinghaus measuring his own forgetting with nonsense syllables. William James distinguishing primary and secondary memory. Bartlett showing that remembering is reconstructive. Hebb proposing that coactive neurons strengthen their connections. Scoville and Milner revealing the role of the medial temporal lobe through H. M. Bliss and Lomo describing long-term potentiation. Loftus demonstrating misinformation effects. O'Keefe and the Mossers revealing spatial maps. Modern researchers identifying engram cells. Each generation remembers the questions of the last and adds new tools. Memory is therefore both the subject of science and the condition that makes science possible. A scientist must remember methods, results, theories, mistakes, and patterns. A field must remember what has been tried, what failed, what remains open. Knowledge itself is a cultural memory, stabilized across books, brains, institutions, instruments, and conversations. The study of memory is one way the brain turns back to examine its own power. Another way to understand memory is to think about cues. A memory is rarely retrieved by force alone. It is usually invited by something: a question, a smell, a place, a photograph, a name, a bodily feeling, a similar situation, a line of music, or a word that touches an old network. Retrieval cues are why memory can feel unpredictable. You may search for something and fail, then have it appear hours later while washing dishes, walking outside, or hearing a completely different conversation. The search system was still moving through associations, and at last one cue found the path. The encoding specificity principle captures this idea. Memory is better when the cues present at retrieval overlap with the cues present at encoding. If a diver learns words underwater, in classic experiments, recall can be better underwater than on land. If words are learned on land, recall can be better on land. Everyday life offers softer versions of the same principle. A classroom, a desk, a notebook, a certain kind of music, or the emotional state of study can become part of the memory's address. State-dependent memory is related. Information learned in one internal state may be easier to retrieve when the body and brain return to something like that state. Mood, arousal, fatigue, intoxication, anxiety, calm, and physiological context can all influence access. This does not mean memories are locked away permanently when the state changes. It means retrieval is probabilistic. The brain uses many signals to find the past, and internal signals are among them. Mood-congruent memory is another pattern. When people are sad, sad memories often become more accessible. When they are anxious, threatening memories and possibilities may come more easily. When they are joyful, positive associations may rise. This can create loops. A mood selects memories that support the mood, and those memories deepen the mood. The brain is not deliberately unfair. It is organizing recall through current emotional relevance. Rumination shows what can happen when memory and emotion become too tightly looped. The mind returns to the same event, phrase, mistake, or fear, not to solve it, but to circle it. Each return may strengthen certain associations while narrowing the frame. In contrast, reflective remembering can widen the frame, adding context, compassion, and new interpretation. The difference between rumination and reflection is not simply whether the past is remembered, but how the memory is used. Prospective memory is the memory of intentions. It is remembering to do something later. Take medication, send a message, bring a document, call someone, turn off the oven, attend an appointment, or ask a question when you see a particular person. It is difficult because the cue often appears while attention is elsewhere. A future intention must survive in the background until the right moment arrives. Much of adult life depends on this quiet system of delayed action. Prospective memory can be time-based or event-based. Time-based intentions depend on remembering at a particular time, such as calling at 6 o'clock. Event-based intentions depend on a cue, such as giving a message when you see a colleague. Event-based cues are often easier because the environment helps. This is why placing an object by the door can work. The object becomes a future memory made visible. Metamemory is memory about memory, the sense of what you know, what you do not know, what you will remember later, and how confident you should be. It is involved when you decide whether to keep studying, when you judge that a name will come back soon, when you feel certain about an answer, or when you know you have forgotten something important. Metamemory is useful but imperfect. People often confuse familiarity with mastery, which is why rereading can feel more effective than it is. The feeling of fluency can mislead learning. When material is easy to process, familiar fonts, clear examples, and immediate repetition can create the impression that it is well learned. But long-term memory may still be weak. Difficult retrieval, delayed practice, and explaining material in your own words provide better evidence of learning. The mind can feel comfortable with something because it is currently present, not because it will be accessible later. Interference is one of forgetting's main causes. Proactive interference happens when old learning disrupts new learning. Retroactive interference happens when new learning disrupts old learning. If you learn a new address, the old one may intrude. If you learn similar vocabulary in two languages, one may compete with the other. Memory is not only a matter of trace strength. It is also a matter of competition among traces. Retrieval-induced forgetting shows that remembering one thing can make related things harder to retrieve. If you repeatedly practice recalling some members of a category, unpracticed related members may become less accessible. This may help the brain reduce competition. To remember efficiently, it sometimes suppresses alternatives. Forgetting, again, can be part of control rather than mere loss. Intentional forgetting is another intriguing area. People can sometimes reduce later recall by being instructed to forget or by repeatedly suppressing retrieval of unwanted material. The mechanisms likely involve executive control systems that limit access to a memory. This does not mean painful memories can simply be deleted by choice, but it does show that memory retrieval is regulated. The mind has gates, not only shelves. The prefrontal cortex is one of the brain's gatekeepers. It helps decide what is relevant, what should be held in mind, what should be ignored, and how retrieval should be guided. When frontal control is tired or impaired, irrelevant memories, distractions, or habitual responses can intrude more easily. This is one reason fatigue can make the mind feel noisy. Memory is not only about traces. It is also about the control of access to traces. The hippocampus itself is not uniform. Different subfields contribute to different computations. The dentate gyrus is often associated with pattern separation, helping distinguish similar experiences. CA3, with its recurrent connections, is often linked to pattern completion, helping a partial cue reactivate a broader memory. CA1 helps compare inputs and relay processed information onward. These divisions are simplified, but they show how memory arises from specialized circuit operations rather than one generic storage function. The entorhinal cortex, sitting near the hippocampus, is a major gateway between the hippocampus and the neocortex. It carries information into and out of hippocampal circuits and contains grid cells important for spatial mapping. In Alzheimer's disease, the entorhinal region is among the early areas affected, which may help explain why navigation difficulties and new memory problems can appear early. The doorway to memory can itself become vulnerable. Navigation and memory are linked in ordinary experience as well. A city you know well is not stored as a flat map. It is stored as routes, landmarks, turns, distances, feelings of neighborhood, and expectations. You may know how to walk somewhere without being able to draw the route accurately. You may recognize a corner only when approaching from one direction. Spatial memory is embodied and partial, built from movement as much as vision. Taxi drivers in large cities have provided famous examples of navigation-related brain plasticity. Studies of London taxi drivers, who must learn a complex map of streets, found structural differences associated with navigational expertise, especially in the hippocampal region. The details and interpretation are nuanced, but the broader lesson is clear. Demanding memory practices can shape the brain. The brain is not a fixed object. It is a history of use. The cerebellum, often associated with movement and coordination, also contributes to learning, timing, prediction, and certain cognitive functions. In motor learning, it helps refine errors and adjust actions so they become smoother. When you learn to catch a ball, play a scale, balance on skates, or adjust a movement to a changed tool, cerebellar circuits help the nervous system predict and correct. Memory is distributed even in skills that feel simple. The basal ganglia contribute to reinforcement learning, action selection, habit formation, and procedural patterns. They help the brain learn which actions lead to rewarding outcomes and which sequences can be automated. This is why habits can continue even when explicit goals change. A cue activates a learned loop. Changing a habit often requires changing cues, rewards, routines, and context, because the memory is embedded in action. The amygdala is often described as a fear center, but that phrase is too narrow. It responds to emotional significance, especially biologically relevant salience, and it modulates memory accordingly. A threatening face, a reward cue, a painful sound, or a socially important signal can engage amygdala systems. Its influence on memory is not simply to make things frightening. It helps the brain prioritize what may matter. Cortisol and other stress hormones follow an inverted pattern in memory. Moderate arousal can strengthen consolidation, but extreme or prolonged stress can impair encoding and retrieval, especially when it disrupts the hippocampus and prefrontal cortex. This is why a calm test environment can matter, and why severe stress may leave a person with vivid fragments but poor sequence. The brain under threat remembers for survival, not for courtroom precision or classroom performance. Acetylcholine is important for attention and encoding. During waking, acetylcholine helps the cortex and hippocampus take in new information. During certain sleep states, the balance of neuromodulators changes, creating different conditions for replay and consolidation. Memory is not only electrical wiring, it is also chemical weather. Different neurotransmitters change how easily networks learn, stabilize, retrieve, or reorganize. Dopamine helps memory by marking value, novelty, motivation, and prediction error. When something is better, worse, or more surprising than expected, dopaminergic systems help update learning. This is one reason curiosity can improve memory. A question creates a gap, and the answer becomes rewarding because it closes that gap. The brain likes resolving uncertainty when the uncertainty is meaningful. Curiosity is a gentle but powerful memory enhancer. When a person genuinely wants to know an answer, the brain's learning systems become more engaged, and even incidental information encountered around the answer may be remembered better. This is one reason wonder matters in educational storytelling. A fact placed after a good question lands more deeply than the same fact dropped without invitation. Memory and attention are also shaped by surprise. Prediction error tells the brain that its model needs revision. If the world behaves exactly as expected, the brain may not store much detail. If something violates expectation, the event becomes informative. A quiet scientific story can use this principle by offering small reversals. Mercury has ice. Venus is hotter than Mercury. Sleep is active. Forgetting can be useful. Confidence is not accuracy. Surprise wakes attention without needing noise. The constructive nature of memory was demonstrated not only by Loftus, but earlier by Frederick Bartlett, who studied how people remembered unfamiliar stories. In his famous work with a Native American tale often called The War of the Ghosts, participants tended to reshape the story over time, making it more familiar, coherent, and culturally expected. They did not simply lose details. They transformed the material through schemas. Memory became a negotiation between the original event and the mind's existing patterns. Schemas help the brain move quickly through the world. In a restaurant, you know roughly what happens: entering, being seated, ordering, eating, paying. You do not have to learn the sequence from scratch each time. But schemas can also create false recall. If people remember a typical office, they may later report seeing books even if none were present, because books fit the office schema. The brain remembers what makes sense, and sometimes what makes sense was not there. Memory for time is surprisingly fragile. People often remember what happened better than exactly when it happened. Events can be telescoped, feeling more recent or more distant than they are. Similar days blend. Distinctive landmarks in time, such as holidays, moves, jobs, relationships, or major news events, help organize memory. Without landmarks, time becomes smooth, and smooth time is hard to divide. This is why routines can make months feel short in retrospect. If each day resembles the last, few distinct markers are encoded. A month of novelty can feel large in memory. A month of repetition can compress. The lived duration of time and the remembered duration of time are different. Memory measures not only minutes, but change. The brain stores sequences as well as isolated moments. Remembering an event often means remembering order. What happened first? What caused what came after? The hippocampus is involved in temporal organization, helping separate similar events that occurred at different times. Without temporal context, memories can become fragments. A fact remains, but its place in life is lost. Temporal context also explains why a memory can feel like a chapter. A school year, a relationship, a job, a city, a period of illness, or a season of work becomes a container for many episodes. Later, a single cue can open the whole period. You do not remember only one day. You remember the atmosphere of an era. Autobiographical memory is built from nested timescales, moments inside days, days inside chapters, chapters inside a life. Memory for pain is complex. People do not always remember pain as an average of every second. They may remember its peak and its ending strongly. This peak in pattern can influence later choices. A painful experience that ends gently may be remembered differently from one that ends badly, even if the total pain was similar. The brain summarizes experience in ways that guide future behavior, but those summaries are not simple measurements. Reward memory can also be imprecise. The brain may remember the anticipation of a reward, the social context, the relief, or the ending more than the objective outcome. This is why habits and desires can survive disappointment. The memory of wanting may be stronger than the memory of satisfaction. Learning systems are not perfect accountants. They are emotional predictors. Memory for dreams is usually weak because the neurochemical and attentional conditions of dreaming are not ideal for later encoding, and because waking introduces rapid interference. Yet some dreams are remembered vividly, especially if emotionally intense or if a person wakes during or soon after them. Dream recall shows again that experience alone is not enough. For something to become a memory, the brain must encode it into a system available to waking recall. Lucid dreaming, when a person becomes aware they are dreaming while the dream continues, is an unusual state where metacognition enters the dream. It has been studied scientifically, though much remains uncertain. For memory science, it is interesting because it shows how different layers of awareness can appear in sleep. The sleeping brain can create a world, and sometimes part of the mind can recognize that world as constructed. Memory can be enhanced by imagery because images provide rich associations. A concrete image is usually easier to remember than an abstract phrase. This is why memory techniques often make information vivid, strange, emotional, spatial, or humorous. The brain remembers the unusual because it stands out from background regularity. A dull fact can become memorable when attached to an absurd picture in a familiar place. Dual coding, the use of both verbal and visual representations, can support learning. A concept represented in words and in an image has more retrieval paths. Diagrams, gestures, metaphors, and examples can make abstract material more memorable because they give the brain multiple formats. Good explanation is not only accurate, it is memorable because it gives the mind handles. Analogies are memory tools too. If a synapse is compared to a conversation, if working memory is compared to a lamp, if the hippocampus is compared to an index, the analogy is not the science itself, but it helps the mind hold the science. The risk is oversimplification. A good analogy should open understanding without pretending to be exact. Memory uses metaphor, and science must use metaphor carefully. Emotionally neutral repetition can create familiarity, and familiarity can create preference. This is the mere exposure effect. Repeated exposure to a stimulus can make it feel more likable, even without conscious memory of the exposure. A melody, face, brand, word, or pattern may become comfortable simply because the brain has processed it before. Familiarity feels safe, and safety can feel pleasant. But familiarity can also create illusions of truth. Statements repeated often may feel more true, even when repetition provides no evidence. This matters in media, politics, advertising, and rumor. The memory system uses fluency as one cue among many, but fluency can be manipulated. To think clearly, a person must sometimes ask not only whether something feels familiar, but why it feels familiar. Memory for moral and emotional events can be influenced by current beliefs. If a person now sees themselves as confident, they may remember earlier events as steps toward confidence. If they see themselves as unlucky, the same events may be remembered as evidence of misfortune. Autobiographical memory is not a neutral database. It is interpreted through identity, and identity is interpreted through memory. Children's memory develops in conversation. When caregivers ask open questions, elaborate on events, name emotions, and build narratives, children learn how to structure memory. They learn that experiences can be told, sequenced, interpreted, and shared. The development of autobiographical memory is therefore not just brain maturation. It is also social apprenticeship and storytelling. Adolescence is a powerful period for memory because the brain is changing, the social world is intense, and identity is forming. Rewards feel vivid, peers matter deeply, risks can feel different, and first experiences accumulate. Memories from this time can remain central for decades because they are tied to becoming. A first friendship, first failure, first independence, first love, or first private dream may become a landmark around which later memory organizes itself. The memory of the future can also become part of identity. People remember hopes they once had, plans they abandoned, and futures they imagined but never lived. These unrealized futures can carry emotional weight. A person may grieve not only what happened, but what did not happen. The brain stores possibilities too, especially when they shape choices. Regret is memory with a counterfactual attached. It remembers an event and simulates an alternative. If only I had said this, chosen that, left earlier, stayed longer, noticed sooner. Counterfactual thinking can teach, but it can also trap. The brain uses imagined alternatives to guide future behavior, but it must also learn when no further learning is possible and the memory can be placed down. Gratitude is another way of revisiting memory. When a person deliberately remembers what helped, who showed up, what beauty appeared, or what was survived, the emotional weighting of memory can shift. This is not pretending everything was good. It is broadening recall so that pain does not become the only organizer. Memory is selective. Attention can influence what is selected for return. Aging can bring a positivity effect in some circumstances, where older adults attend to and remember positive information relatively more than negative information. The reasons are debated and may involve emotion regulation goals, attention, and motivation. It suggests that memory across the lifespan is not merely decline. It is also changing priorities. A mind that has lived longer may choose differently what deserves rehearsal. There are rare and fascinating memory conditions. Some people have highly superior autobiographical memory, recalling dates and personal events with extraordinary detail. This is not the same as having perfect memory for everything, and it can come with burdens as well as gifts. Other people have severely deficient autobiographical memory, living normal lives while recalling personal past events with little vivid imagery. Human memory varies more than common assumptions suggest. Aphantasia, the inability or reduced ability to form voluntary mental images, also changes the texture of memory for some people. A person may remember facts about an event without seeing it in the mind's eye. Others have vivid visual imagery. Memory is not experienced the same way by everyone. Some remember in pictures, some in words, some in spatial feelings, some in emotional summaries. The archive has many formats. Synesthesia can link memory and perception in unusual ways, such as letters associated with colors or sounds with shapes. These associations can sometimes support memory because they add extra cues. A number may not be only a number. It may have a color or personality. The brain's mapping systems can vary, and memory uses whatever stable associations are available. Photographic memory, in the popular sense of a perfect internal camera, is mostly a myth. Some people have exceptional memory abilities, and eidetic imagery has been reported especially in children. But human memory does not generally preserve pages, scenes, or events with flawless visual accuracy. Even memory champions rely on strategies, structure, and practice rather than a magical camera. The real science is more interesting than the myth because it shows how skill can transform ordinary memory systems. Memory athletes demonstrate the power of encoding, imagery, and retrieval structure. To memorize a deck of cards, they do not usually stare harder. They translate cards into people, objects, actions, or images, then place those images along a familiar route. What looks like impossible memory is often disciplined use of very human capacities: spatial memory, visual imagination, association, and practice. The brain remembers best when information becomes meaningful and located. There is a boundary between memory improvement and memory obsession. A life does not require every detail to be retained. Some forgetting allows forgiveness, privacy, updating, and rest. The goal of understanding memory is not to turn the mind into a perfect database. It is to appreciate how remembering works, how learning can be supported, and how gently the brain carries what it can. In laboratories, researchers study memory with word lists, mazes, images, tones, brain scans, electrophysiology, molecular tools, and clinical cases. But outside the laboratory, memory is woven through ordinary acts. Recognizing a friend's walk from far away, making tea the way someone taught you, avoiding a street where something bad happened, smiling at a joke whose setup began years ago, knowing the next line of a song before it arrives. The ordinary nature of memory is part of its wonder. It does not announce itself every time it works. It simply lets the world make sense. It gives continuity to objects and people. It lets a cup remain a cup when you look away and back. It lets a loved person remain themselves across changes in hair, age, mood, and clothing. It lets language unfold because the beginning of a sentence remains active until the end arrives. Memory also allows trust. You trust that the floor will support you because it has before. You trust that a friend is kind because memory has accumulated evidence. You trust that fire burns, that winter returns, that a certain path leads home. The future is never known completely, but memory gives it structure. Without memory, every moment would be new, and newness without continuity would be terrifying. This is what made HM's life so poignant. He was intelligent, polite, and present, but the present could not accumulate. The stream of experience did not become a continuous river. People he had met many times remained new. Events did not settle into history. His case taught neuroscience, but it also revealed the human tenderness of memory. To remember someone is to let them continue with you. The medial temporal lobe is not the only part of the brain important for explicit memory. The neocortex stores distributed knowledge. The thalamus and mammillary bodies are involved in memory circuits, and damage there can produce severe amnesia, as in Korsakoff syndrome, often associated with thiamine deficiency. The frontal lobes help organize recall. Memory depends on networks, and damage at different points can produce different forms of forgetting. Korsakoff syndrome shows that memory failure can include confabulation, where a person produces false explanations or stories without intending to deceive. The brain tries to make sense of gaps. When monitoring systems fail, invented material can feel real. Confabulation is not ordinary lying. It is a disorder of memory and self-monitoring, revealing how strongly the mind seeks coherence. Semantic dementia, associated with degeneration of anterior temporal regions, can erode conceptual knowledge. A person may see an object but no longer know what it is called or what category it belongs to. Words lose meaning. Familiar things become puzzling. This differs from hippocampal amnesia, where new episodes fail to form. Different diseases reveal different architecture, as if damage lights up the hidden divisions of memory by removing them. Parkinson's disease can affect memory and cognition through basal ganglia and frontal circuits, especially in learning from feedback, executive function, and working memory. Huntington's disease, traumatic brain injury, stroke, epilepsy, depression, sleep disorders, and many other conditions can also alter memory. The memory system is not one organ with one disease. It is a network vulnerable through many routes. Depression often changes memory by biasing recall toward negative material and making positive memories harder to access vividly. It may also impair concentration, sleep, and motivation, which weakens encoding. This can create the painful impression that life has always been bleak. Treatment, social support, and recovery can change not only mood but access to memory. When mood shifts, the remembered past can become wider. Anxiety can make memory future-facing in an exhausting way. The mind searches past events for threats and builds simulations of what could go wrong. This is memory-serving prediction, but under fear it may overpredict danger. The same capacity that allows planning can become worry. Again, the memory system is not malfunctioning randomly. It is doing a protective job too intensely. Attention deficit conditions can affect memory indirectly. A person may feel they have a bad memory when the primary difficulty is encoding. If attention was not stable when the information appeared, there may be little to retrieve later. This is why external supports, routines, reminders, and environmental structure can help. They reduce the burden on working memory and prospective memory. Memory is also affected by sleep deprivation. Poor sleep can impair attention before learning, weaken consolidation after learning, and reduce emotional regulation, which then affects what is encoded and how it is retrieved. A tired brain may still function, but its memory systems are working under strain. Sleep is not a luxury added after learning. It is part of the learning cycle itself. Alcohol can produce blackouts when it disrupts the formation of new long-term memories, even while a person remains awake and active. During a blackout, behavior may continue, but the hippocampal-dependent recording of events is impaired. This distinction is important. Consciousness at the time does not guarantee later memory. The brain must encode experience into durable traces, and some substances interfere with that process. Anesthesia, seizures, concussion, and certain medications can also disrupt memory formation or retrieval. The fragility of memory around medical events shows how dependent remembering is on brain state. A person may be present, responsive, or partially aware, yet later have little explicit memory. Consciousness and memory overlap, but they are not identical. Memory after concussion often shows a gap around the injury. Retrograde amnesia may erase moments before the event, and anterograde amnesia may affect moments after. The brain's ability to encode and consolidate is disrupted by trauma. This is one reason immediate reports after accidents can be incomplete. The mind may not have had the conditions needed to store the event normally. The ethics of memory modification are increasingly important. If reconsolidation can reduce fear, that could help trauma treatment. If drugs or stimulation could alter memory strength, questions arise. What should be softened? What should be preserved? Who decides? And what happens to identity when painful memories change? Relief matters, but memory also carries truth, responsibility, and meaning. The science is powerful because memory is personal. Optogenetics in animals has shown that specific memory-related cell ensembles can be activated or altered, but this does not mean human memories can be edited like text files. Popular culture often jumps too quickly from mouse experiments to fantasies of memory deletion. The real findings are remarkable enough. Memories correspond to physical patterns that can sometimes be identified and manipulated in controlled laboratory conditions. The human meaning of memory remains far more complex. Brain imaging has shown that remembering reactivates some of the same sensory and conceptual regions involved in perception. Imagining a face and seeing a face are not identical, but they can share neural resources. Remembering a sound can engage auditory areas. Remembering movement can engage motor-related systems. Recall is partial reperception, guided from within rather than from the outside world. This is why vivid memories can affect the body. Remembering embarrassment can make the face warm. Remembering fear can tighten the chest. Remembering love can soften the body. The brain areas that reconstruct memory interact with systems that regulate emotion, autonomic responses, and action readiness. A memory is not a ghost floating above biology. It is biology re-entering a pattern. Mind wandering often draws from memory. When the external task is undemanding, the default mode network becomes more active, supporting autobiographical thought, future simulation, social imagination, and self-referential processing. This network includes medial prefrontal, posterior cingulate, parietal, and temporal regions, interacting with the hippocampal formation. The resting mind is not empty. It is often traveling through time. The default mode network helps explain why quiet moments can fill with old scenes and imagined futures. A bus ride, a shower, a walk, or the minutes before sleep can open internal space. The mind rehearses, repairs, predicts, regrets, hopes, and remembers. This inner travel is one of the brain's characteristic activities. External stillness does not mean internal stillness. Memory has rhythms across the day. Attention, alertness, hormone levels, body temperature, and sleep pressure all change. Some people encode best in the morning, others later. Emotional memories may be processed differently depending on stress and fatigue. The brain is not the same instrument at every hour. It is tuned by circadian rhythms and by the history of the day. The hippocampus is sensitive to novelty and exploration. New environments can engage it strongly, which may be why a walk through an unfamiliar place can feel mentally bright. Exploration is learning in motion. The brain maps space, predicts turns, marks landmarks, and records surprises. Curiosity and movement meet in the hippocampal system. Memory and imagination can blur in childhood play. A child may remember a pretend world with emotional vividness because the brain systems of imagery, story, and feeling were deeply engaged. Adults also carry memories of imagined experiences. Books, films, games, dreams, and fantasies can leave traces that feel meaningful even though they were not lived physically. The brain stores experience, and experience includes inner worlds. Reading is a special form of memory-guided simulation. The marks on a page evoke sounds, meanings, images, emotions, and predictions. You remember earlier sentences to understand later ones. You build scenes from words. Later, you may remember a fictional place almost like a place you visited. Literature uses memory's constructive power deliberately, inviting the brain to create what the eyes never saw. This also means stories are easier to remember than disconnected statements. A story provides sequence, cause, intention, emotion, and imagery. Human memory is tuned for agents acting in worlds. A scientific explanation that unfolds as a story of discovery, rather than only listing facts, fits the grain of memory. The mind remembers not only information, but movement through meaning. The brain can also remember absence. A missing object in a familiar place can stand out because the schema predicts it should be there. A silent phone can feel loud when a message was expected. An empty chair can hold a person in memory. Absence is not nothing to the brain. It is a violated expectation, and expectation is built from memory. Place cells and grid cells make spatial memory seem elegant, but they are not tiny GPS devices in the technological sense. They are biological signals embedded in moving, sensing, motivated animals. They respond to environments, goals, boundaries, speed, direction, and experience. The brain's map is not a cold coordinate sheet. It is a map for action. The immune system also has memory, though it is different from neural memory. After exposure to a pathogen or vaccine, immune cells can respond faster to future encounters. This is not remembering a birthday or a face, but it is biological learning from the past. The body contains multiple memory-like systems: neural, immune, cellular, epigenetic in limited contexts. Life persists by being changed by experience. Plants do not have brains, but they can show forms of physiological memory, such as responses altered by prior stress, light exposure, or seasonal conditions. This should not be romanticized into human-like remembering, but it reminds us that memory, broadly understood as history-dependent change, is a deep principle in biology. Nervous systems made it fast, flexible, and experiential. Artificial intelligence has introduced new metaphors and new confusion around memory. A computer can store data exactly, and a model can adjust parameters based on training, but human memory is neither a hard drive nor a simple database. It is embodied, emotional, reconstructive, and tied to consciousness. Comparing brains and machines can be useful if done carefully, but the differences are as important as the similarities. One difference is that human memory has stakes. To remember is not just to retrieve information. It can change mood, identity, relationships, and choices. A database does not miss someone. A person does. A file does not feel nostalgia. A brain does. Memory matters because it is woven into value. The ethics of digital memory are becoming part of ordinary life. Messages, photographs, location histories, and social media posts preserve versions of us that may outlast their original context. Digital records can support memory, but they can also trap people in old selves or revive pain unexpectedly. Biological memory forgets partly by design. Digital systems often preserve by default. Human life may need both remembering and forgetting. There is wisdom in selective forgetting. Not every embarrassment needs to remain vivid. Not every argument needs to be rehearsed. Not every fear deserves renewal. The brain naturally lets many details fade, and sometimes this fading is mercy. A perfect memory might not be a blessing. It might be a life with too little distance. Forgiveness may involve memory changing its emotional charge. It does not always mean forgetting the event or denying the harm. It may mean the memory no longer dominates future responses in the same way. The past is still known, but its grip loosens. This is another example of memory as a living relation, not a fixed object. Learning from mistakes requires a careful balance. If a mistake is forgotten completely, it cannot guide. If it is remembered only with shame, it can paralyze. Useful memory preserves information without freezing the self inside the error. The brain is at its best when it can say, "This happened, this mattered," and something can be learned. Memory for success can matter just as much. People often remember failures more sharply than quiet competence. But confidence depends on access to memories of coping, learning, finishing, repairing, and enduring. A mind that cannot retrieve its own evidence of strength may underestimate itself. Remembering well is not only avoiding error. It is keeping a truthful record of capacity. Some memories are stored socially because one person cannot hold all of them. In couples, families, teams, and communities, people develop transactive memory systems. One person remembers birthdays, another knows finances, another knows routes, another remembers stories, another remembers where objects are kept. The group becomes smarter because memory is distributed. Losing a person can therefore mean losing part of a shared mind. This is why old family stories matter. They carry information, but also belonging. A story told many times becomes a communal memory, even for those who are not there. It can preserve values, warnings, humor, and identity. It can also distort or simplify. Every family, like every culture, has both memory and mythology. Memory and imagination also support empathy. To understand another person, the brain draws on remembered feelings and situations, then simulates what someone else might be experiencing. You may not have lived their exact life, but memory provides emotional materials: fear, hope, loss, embarrassment, relief. Empathy is not only moral intention, it is memory used beyond the self. The future of memory science may involve more precise tools for observing and influencing neural circuits, better treatments for dementia and trauma, improved educational methods, and deeper understanding of sleep. But the field will probably remain humble because memory touches consciousness, identity, and meaning. The more precisely scientists describe mechanisms, the more remarkable the lived experience becomes. A memory can be studied as synaptic plasticity, hippocampal indexing, cortical reinstatement, emotional modulation, and retrieval cueing. But it can also be the sound of rain on a roof in a childhood home. Both descriptions are true at different levels. Science does not make the personal version smaller. It reveals how much had to happen for such a simple moment to remain. Memory is also shaped by the simple fact that the brain has limited energy. Neural activity is metabolically expensive, and synaptic change must be regulated. A system that strengthened every connection equally would soon lose selectivity. This is why sleep, inhibition, forgetting, and synaptic downscaling are important ideas in memory research. The brain must preserve what matters without allowing every day's noise to become equally loud. Learning is not only addition, it is tuning. Inhibition is one of the quiet heroes of memory. To retrieve one word, the brain must suppress competitors. To focus on one task, it must quiet irrelevant associations. To update a belief, it must reduce the pull of older patterns. Inhibition is not merely stopping action, it is sculpting thought. When inhibition weakens through fatigue, stress, age, or frontal dysfunction, memory can become cluttered with intrusions. What is remembered may not be wrong, but it may be poorly controlled. The balance between pattern completion and imagination can make memory feel real even when it is partly constructed. A partial cue activates a network, the network fills in missing parts, and the filled-in scene arrives with sensory and emotional detail. Most of the time, this is useful. It lets a few fragments retrieve a meaningful whole, but it also means that the mind can complete patterns too confidently. Memory strength is inseparable from its risk. There is a difference between accuracy and usefulness. A memory of a childhood home may contain incorrect dimensions, missing furniture, or impossible light from 2 different seasons, yet still be useful as a record of belonging. A memory of a lesson may not preserve the exact words of the teacher, but it preserves the idea. The brain often stores gist before detail, meaning before measurement. Scientific accuracy matters when facts are needed, but personal memory also serves emotional and narrative truth. Gist memory can be remarkably durable. People may forget the details of an article, but remember its conclusion. They may forget a conversation's exact phrasing, but remember the agreement. They may forget individual examples, but remember the principle. This is efficient because life rarely requires exact replay, but it can cause problems when exact details do matter, such as in legal testimony, medical instructions, or technical learning. The brain's natural preference for meaning must sometimes be supported by notes, recordings, and careful review. Memory is strengthened when information is generated by the learner. This is called the generation effect. People often remember material better when they produce it themselves rather than simply read it. Completing a word, explaining an idea aloud, solving a problem before seeing the answer, or making an example creates deeper encoding. The brain remembers participation better than reception. It is not only exposed to information, it has acted on it. Elaboration works for similar reasons. When new information is connected to why, how, when, where, and what it resembles, it becomes part of a richer network. A name linked to a face, a profession, a meeting place, and a visual image is easier to retrieve than a name repeated mechanically. Elaboration gives memory roots. The more meaningful roots a memory has, the more ways the mind has to reach it later. But memory can also be overloaded by excessive detail without structure. A dense lecture, a crowded page, or a rapid list of facts may contain valuable information, yet leave little behind if the mind has no framework. The brain needs pacing, categories, examples, and pauses. Even in science, calm structure helps memory. A fact becomes more memorable when the mind knows where to put it. This is why the science of memory is also a lesson in gentleness. The brain learns through repetition, sleep, meaning, curiosity, and time. It does not need to be forced into remembering everything at once. It can return, strengthen, link, and refine. A memory formed tonight may not be finished tonight. It may continue changing quietly after the lights are off. And perhaps this is the most restful part of the subject. The brain has been doing this work for you your entire life. Long before you knew words like hippocampus, synapse, consolidation, or engram, your brain was learning faces, voices, smells, movements, routes, dangers, comforts, and meanings. It was building the world from repetition and surprise. It was making home familiar. It was making language possible. It was making you continuous. Memory is also personal in its silence. Many of its most important operations happen without announcement. The familiarity of a hallway, the ease of a practiced movement, the expectation that a sentence will end grammatically, the quiet recognition that a friend's mood has changed. These are not dramatic memories, but they are the fabric of intelligence. They let the world feel continuous rather than chaotic. They let the present arrive already partly understood. At night, memory changes its tone. The day's events may loosen from their practical urgency. A sentence someone said may return. An old scene may appear unexpectedly. The mind may wander through fragments, not in chronological order, but by association. One thought leading to another, one image opening into another. This drifting is not meaningless. It is one of the ways the brain moves through its own networks when external demands become quiet. Some memories arrive only when the world is still. During the day, attention is occupied. At night, with fewer tasks, the mind may hear itself more clearly. This can be peaceful or uncomfortable. But even when the mind wanders, it is showing the same associative machinery that allows memory to connect, consolidate, and create. The brain is never only a calculator. It is a living archive that speaks in images, sensations, and stories. If there is a central lesson in memory science, it may be this: remembering is active. The brain selects, encodes, strengthens, links, updates, retrieves, and sometimes transforms. It forgets in order to function. It distorts because it constructs. It preserves because the past matters. It lets go because the present matters too. Memory is not a flaw-filled version of recording. It is a different kind of intelligence. And right now, while you rest, your brain is still doing quiet work. Some traces from the day may be weakened. Others may be replayed. New information may be woven into old knowledge. Emotional tones may soften or settle. Skills may become a little more fluent. A thought that felt scattered may find a place. You do not need to direct all of it consciously. Much of memory's work happens beneath awareness, patiently, biologically, in the dark. The archive of a life is never complete, and it does not need to be. It is enough that certain things remain. The sound of a loved voice, the meaning of home, the lessons that kept you safe, the skills your hands know, the words that shaped you, the places that changed you, the quiet proof that you have moved through time and carried some of it with you. Memory is the past still participating in the present. It is the brain's way of saying that what has happened does not vanish completely. Some of it becomes knowledge. Some becomes warning. Some becomes tenderness. Some becomes the self. Sleep well. Good night.